Welcome back to The Explainer. If you've ever worked on a speech recognition pipeline, you probably know that treating audio like isolated, independent chunks of data is a fast track to a massive, system-breaking bug. It just fundamentally misrepresents reality. Today, we're going to look at the Kaldi tri1 training stage through the lens of a classic software engineering scaling problem. We'll explore how Kaldi fixes this architectural flaw by upgrading from simple monophones to context-aware triphones, how that seemingly innocent transition triggers an explosive data scaling crisis, and how a brilliant algorithmic concept called the CNONE swoops in to solve the whole thing. Here is our roadmap for today. We'll quickly hit the context bug, modeling triphones, the state explosion, the CNONE solution, phonetic decision trees, and finally wrap up with pipeline integration. Let's jump right in.
Section 1, the context bug. So, we have to start by identifying the critical flaw in our previous monophone models. They literally ignore their neighboring phonemes. From a developer's perspective, imagine writing a text parser that reads a string but completely strips out the spaces and punctuation, totally ignoring how words connect to each other. Well, that is essentially what monophones are doing to our audio data.
When you look at the monophone approach versus the triphone CNONE approach side by side, the architectural shift is huge. A monophone model operates totally independently. It uses exactly one Gaussian mixture model, or GMM, per phoneme, and it is completely blind to the sounds coming before or after it. But the triphone CNONE model, it's highly dependent. It tracks the left and right context and uses shared GMMs across clustered states to map all that complex data.
And the reason this matters, the actual bug here, is a biological phenomenon called coarticulation. Think of coarticulation as data corruption. When we speak naturally, our mouths are honestly kind of lazy. We start physically preparing for the next sound while we're still finishing the current one. So the acoustic properties of a sound actually morph based on its environment. The hard k sound in the word key is produced much further forward in your mouth than the k in ka. To a monophone model, this just looks like noisy, corrupted data, because it's stubbornly trying to force both of those different acoustic signals into the exact same statistical bucket.
Section 2, modeling triphones. To patch this bug, we have to upgrade to triphones, purposefully bringing in the immediate left and right context. Let's use a real-world example to see how this works in practice. Take a simple string like the word cat. Instead of modeling a generic K, an A, and a T, we're going to chop it into 3 context-rich chunks. We use the notation L minus P plus R. So our first triphone is silence minus K plus A. That translates to the phoneme K, given that there is silence to its left and the vowel A to its right. We do the same thing for the middle vowel and then the closing consonant. By doing this, we are massively enriching our data model with crucial environmental context.
Section 3, the state explosion. But, as any developer knows, solving one major bug usually creates another. By adding all this context, we've inadvertently built a massive computational bottleneck.
Mathematically, modeling every possible left phone-right combination is an exponential nightmare. English has roughly 40 base phonemes. Multiply those together, 40 times 40 times 40, and boom, we suddenly generate about 64,000 possible triphones.
And unfortunately, it gets worse. In a standard hidden Markov model, each phoneme is broken down into 3 distinct states, basically the beginning, middle, and end of the sound. So multiply our 64,000 triphones by 3, and our state space violently explodes to nearly 192,000 individual states. This triggers a massive out-of-memory style crash called the zero data problem. The reality is, most of the 64,000 triphone combinations literally do not exist in the English language. You could have the biggest audio corpus in the world, and you still wouldn't have enough data to satisfy every combination. If the system hits a rare or totally unseen triphone during training, it doesn't have the data to estimate a GMM, and the pipeline essentially crashes or spits out garbage parameters.
Section 4, enter the sapone. So how do we fix this out-of-control state space? We bring in one of the absolute coolest algorithms in speech recognition.
Enter the CNONE. Think of the CNONE as a heavy-duty compression algorithm for our state space. Instead of forcing 192,000 individual states to scrounge for their own data, a CNONE groups acoustically similar triphone states together so they can share a single GMM. In Kaldi, you'll see this referred to in the codebase as a PDF ID. This simple clustering concept takes our 192,000 states and compresses them down to a highly optimized 2,000 to 5,000 shared models. Suddenly, every single unit remodeling actually has enough pooled data to train reliably.
Section 5. Phonetic decision trees. But that begs the question, how does the system actually decide which states belong in which phenome cluster? It uses a binary routing system called a phonetic decision tree. For every state of every phoneme, it's basically running a series of linguistic if-then statements. Let's look at the middle state of the vowel ah. The tree asks, is the phoneme on the right a nasal sound? If yes, like in the words can or ban, it routes that state straight to phenome A. If no, it moves down the tree. Is the left phoneme a stop? If yes, like in cat or bat, it routes to phenome B. This logic ensures that sounds with similar acoustics fall into the exact same statistical bucket.
And this is absolutely crucial for the pipeline because it enables really graceful generalization. During training, states cluster up to pool data for robust GMMs. But what happens in production when the system hears a triphone it has literally never seen before? It doesn't break. That unseen triphone just falls down the exact same logic tree, answering yes or no based on its phonetic traits, until it naturally lands in a pre-existing phenome. It just inherits an existing, sensible model. Zero data bug, totally eliminated.
Section 6. Pipeline integration. Okay, let's zoom out. How does this specific tri1 stage wire into the broader Kaldi architecture?
The tri1 stage is really the foundational bridge between naive modeling and advanced optimization. Notice that it's relying on basic 39-dimensional MFCC features. That's your 13 base features plus velocity and acceleration. We aren't applying any fancy matrix transformations like LDA or MLLT just yet. And to even start this whole clustering process, tri1 completely relies on the rough frame alignments from the previous monophone stage to bootstrap itself. It needs those initial hints of where sounds begin and end to start asking the decision tree questions. Here's that bootstrapping loop in action. It takes those monophone alignments to build the tree, it clusters the states, and then it trains the shared GMMs using expectation maximization, specifically the Baum-Welch algorithm. Once those are trained up, it realigns the audio using its brand new, much smarter triphone models, and it repeats the cycle. Finally, it outputs the official phenome definitions and highly accurate alignments for the next stage to consume.
So tri1 brilliantly solves the state explosion. By clustering nearly 200,000 states down into a few thousand phenomes, we finally have a robust, context-aware model that doesn't crash on unseen data. But looking at those raw 39-dimensional MFCC audio features we just used, it does leave us with a bit of a cliffhanger. What kind of mathematical wizardry is the pipeline going to invent next to squeeze even more performance out of those features in the upcoming Tri2B stage? Think on that as you review your notes, and we will unpack that exact problem next time. Thanks for hanging out for this explainer.